Okay, so this video begins chapter 2 for us, and we are moving into the book. Chapter 2 is all about polynomial and rational functions, and the first section focuses on quadratics. Now, you do not have to write this definition, but we need to see it, and we need to talk through it, because it's a really simple math definition. So, and you really don't have to rewrite it, and you don't have to recreate it, okay? So just kind of watch through here. This is the definition of a polynomial function. You have dealt with polynomial functions since pre-algebra. So it's nothing new to us, but wow, the way they've described it. Let n be a non-negative integer. So n is a positive whole number. And let a sub n, that's a subscript, because it's a little lower than the a. So a sub n minus 1, a sub n minus 2, and so on. A sub 2, a sub 1, a sub 0 be real numbers with a sub 0 not equal to 0. So all of these a sub whatevers are just real numbers. They're just variables standing for real numbers, and they're in a little pattern. And the last one they're saying can't be 0. Then the function given by a sub n x to the n. So this is the coefficient of the variable raised to the nth power. So they're just keeping it kind of organized. And then a sub n minus 1 times x to the n minus 1. So they're just keeping these, that's the n minus 1th coefficient. So, and then we've got another coefficient times x to a power until we get to something here that's a little more familiar. So if it's a real number times x to a power plus a real number times x to a power plus a real number times x to a power, as many times as they want to do it, until we get to just a real number, then that's a polynomial function. So it's quite confusing looking. But if I pick up with you with, let's do a sub 4 x to the 4. Is that the way I want to do it? Yeah. And then a sub 3 x to the 3, and then a sub 2 x to the 2, and a sub 1 x to the 1, and then a sub 0. So this is my n, because it's the highest power. And then 3 is 1 less than 4, so we would call that n minus 1. And 2 is 2 less than 4, so we would call this n minus 2. So everything is based on that first term's power. And 1 is 3 less than 4, so that would be a to the n minus 3. And then a sub 0 would be a to the n minus 4. And then if you put n equal to 4 in here, then that all kind of would make sense. That's a to the 4x to the 4. This would be a to the 4 minus 1, x to the 4 minus 1. This would be 4 minus 2. Let me erase this one. Well, this one is 4 minus 3. And then this last one is 4 minus 4, which is where that a to the 0 comes from. And it's also x to the 0. And anything to the 0 powers 1. That's why they just end with calling this a to the 0. So this is just a polynomial. This is like some real number times x to the 4th, plus some real number times x to the 3rd, plus some real number times x squared, maybe minus a real number times x to the 1, and then we have a constant. So that's just a polynomial. It's just a super confusing way to talk about it. But it's one that it's worth us seeing, because you may see stuff like that in the future and in other math classes. And I think they even show us something like that later. But okay. So polynomial functions are classified by degree. The degree is the highest power of the variable in the equation. Well, let's say in the function. And that's assuming there's only one variable. It's kind of a different rule if there's more than one variable in the function. All right, so if we have this first function, which is f of x equals a, and they tell us a is not 0, and remember a was just a real number, so the example might be equals 7. Then this is the constant function, because it doesn't have a variable. And it does not have a variable. That's what I just said. Whoops, now I'm repeating myself. But I could think of it as being made x times x to the 0 power. So this is a 0th degree. It's a constant function. It's a horizontal line. The line y equals 7 goes to 7 on the y-axis and crosses the y-axis. Okay, the next function we're going to talk about is f of x equals, and they use, do they use mx plus b? Yeah, mx plus b. As long as m is not equal to 0. This is a linear function. You're very familiar with those. The degree of the function is a 1 because that is the power of the x. So it's a first degree. If you have f of x equals ax squared plus bx plus c. This is a quadratic function. You're also very familiar with those. And our degree is 2 because 2 is the highest power of the x. All the x's in here. This has a 1, but 2 is the highest power. So this is a second degree. And then we could keep going. We could talk about a third degree and a fourth degree and a fifth degree, but today's all about quadratics. All right, we're going to do a deep dive into the parent quadratic. In fact, throughout the year, we're going to be doing a deep dive into most of the families that we had in Chapter 1. The absolute value, the square root, the rational. So most of them, we're going to be doing a deep dive. So if we have the parent function for the quadratic, we're going to call it ax squared. And we're going to talk about if a is greater than 0. Actually, let's just do x squared. Then we would be able to build a graph for that. If x is 0, y is 0. If x is 1, y is 1. If x is 2, y is 4. Just plugging in, making a little table. If x is negative 1, y is 1. If x is negative 2, y is 4. And that's because quadratics have symmetry. And the parent has symmetry with the y-axis. All right, we can talk about its domain. Now, domain is x. So we can think this would keep spreading out to negative infinity on the x, and it would go to positive infinity on the x. So the domain is negative infinity to infinity. Range is y. So we could label for the y-axis, it's not going to get all the way down here to negative infinity. It doesn't even start having values until 0, but it does go all the way up to positive infinity. So the range is 0 to infinity. We really probably shouldn't put this x and this y. I was just kind of trying to talk about domain being x, range being y. Okay, it has an x-intercept. If you let y be 0 and solve for x, then you can take the square root of both sides and you get 0 because there's no plus or minus 0. It has a y-intercept. The test is let x equal to 0. So it has a y-intercept at 0. Let's talk about where it is decreasing and increasing. Now remember, decreasing and increasing use x variables. So when we look at this graph from left to right, we start here and we are decreasing. And then we hit this minimum point and we begin increasing. And because we know that that's the intercept, we know the minimum point is 0, 0. So we use x values for decreasing and increasing. So I've already got my x-axis labeled. I've got my farthest, my minimum point, and then my farthest to the right. So we decrease from negative infinity to 0, and we increase from 0 to infinity. And decreasing and increasing intervals are always parentheses. Now let's decide if it's even, odd, or neither. I'm going to erase this side so we can talk more. Well, we have tests for even, odd, and neither. We will do f of negative x and c. Well, we plug a negative x in and we square it, we get a positive x squared. That's exactly the same. So this is an even function, which has symmetry with respect to the y, which sure does look like it has symmetry with the y. The axis of symmetry is the y-axis. It's also the line x equal to 0. The y-axis is the line x equal to 0. And we have some extrema. We don't have any absolute max because it goes on forever, so to infinity. But we do have an absolute minimum right here. We have an absolute minimum at 0, 0. So we didn't have to calculate it on the calculator because it's the parent function. All right. And then just a couple things like since if we wanted to think of it as being a x squared, so since it's just x squared, a would be 1. So that 1x squared is the same thing as x squared. So our a is 1. And since a is positive, then that means it opens up like that and it's praising. I think that's about it. Oh, we could also call that absolute minimum the vertex. So it has a vertex at 0, 0. All right, so we know a lot of stuff about it using all that terminology from chapter 1. Alrighty. So, example 1. Sketch the graph and describe how the graph is related to the parent. F of x equals x squared, because we are just focusing on quadratics right now. All right, so there's our parent, and A part wants us to sketch the graph, and we have g of x equals negative x squared plus 1. So it's all the transformations that we practiced in chapter 1. The negative is in front of the x squared, so that's a reflection on the x-axis. That 1 is being added to the whole function, so it's moving it up 1. So we really want to get the pattern for x squared in our head. We got 0, 0, 1, 1, 2, 4. And then we have symmetry, so we also have negative 1, 1, and negative 2, 4. So we really want to get that in our head so that we can make a quick sketch of this. Well, it's up 1, so my vertex got moved up 1, but then it got flipped over. So this is like the vertex point at 0, 0, but then we would have these points right here, and then we would have 2 at 1, 2, 3, 4 down from the vertex. So we would have points 0, 1, negative 1, 0, and negative 2, negative 3. All right, let's do B part. Let's describe how it is related to the parent. All right, so that 2 is inside affecting the x, so it's a horizontal, that left-right shift, and it's the opposite of what it looks like, so it is left 2. And that 3 is affecting the whole function, so minus 3 is down 3. So this time, it's not a reflection, it's just a left and a right shift, so it's going to move my vertex. Instead of being at 0, 0, it's going to move it left 2 and down 3. So my vertex is now here. That's where my old 0, 0 was. And then I had 1, 1, so it's like up 1 and over 1 from there, up 1 and over 1 from there. And then you also had that 2, 4, so it was over 2 from there and up 4, and over 2 from here and up 4. So the pattern, well, I think I missed almost every one of those points. That sort of looks like a little teddy bear. Okay. All right, standard form of a quadratic. F of x equals a parenthesis x minus h squared plus k. This is the standard form of a quadratic. I will often call it the vertex form because from this form you can get your vertex, which is your h comma k. And it's just sitting right here. All right, so we're going to do an example, and we're going to take a quadratic and we're going to identify the vertex. Describe the graph and identify the vertex. Let's go to the next page. All right, so we have f of x equals 2x squared plus 8x plus 7. Actually, I don't think you all have had experience with this before. Let's make it nicer. X squared plus 8x plus 5. All right, if they want us to identify the vertex, then we've got to get it into the vertex form. So what we're going to do is we're going to complete the square.
You're supposed to go home.
Okay, I think I was saying we needed to write it in vertex form. So first thing we're going to do, write in vertex form by completing the square. You all had a really big quadratics chapter in Algebra 2, but I believe Ms. Brandon decided to skip the chapter on completing the square because I always have to hit it really hard for pre-calculus, and that quadratics chapter was already so big. So here's what we do to complete the square. It's just some simple steps that you got to follow with me every time, and then you're going to get the process down. So the first thing is we're going to group these first two terms together, okay? So these first two terms are together, and this needs to be a 1. Ours is. If it isn't, there's a step we have to do. So we're going to rewrite. Okay, I think I said we needed to group these first two things together. My video just kind of messed up a little bit. And this term right here needs to have a 1 in front of it. If it's not, we'll have to do something different. So let's rewrite. We have x squared plus 8x. We do a blank. Then we do the plus 5. And then we do a blank after it. So first, to write it in vertex form, we complete the square. We rewrite, adding the blanks. And third, now we're going to do b over 2, and we're going to square it. So remember that this was I thought we wrote it somewhere. Yeah. Ax squared plus bx plus c. B is the coefficient of the x. So 8 is our b. This is ax squared plus bx plus c. So we're going to do 8 over 2, and we're going to square it. I always ignore this sign here. Whether it's a plus or a minus, I just ignore it because we're going to square it anyways. So if it's negative and we square it, we get a positive. If it's positive and we square it, we get a positive. So I just ignore it. So 8 over 2 is 4 squared, and 4 squared is 16. Now we're going to take it, and we're going to add 16 here, and we're going to subtract 16 here. Add and subtract that number in the blanks. And we rewrite it with blanks. Okay, get our little steps right. So what happens when we add 16 and we subtract 16? Well, we didn't change it at all. That's equal to 0. But it helps us because we have created a perfect square trinomial. And this is going to factor beautifully every time. So you can do the X method on that. With just those three terms there, you can put your AC at the top, your B at the bottom, and it's always going to factor to the same number there, 4 and 4. So it's x plus 4 times another x plus 4, or x plus 4 squared. And then you add these two together, and you get negative 11. Now it's in, you've just completed the square. Now it's in vertex form. So we've got our f of x equals x plus 4 squared minus 11. So I told you over here, the vertex was sitting right there as our hk. So vertex form is a parenthesis x minus h squared plus k. So the vertex for this problem is actually negative 4, comma, negative 11. This one is always the opposite of what it looks like, right? That's actually a left shift, and this is down 11. So that vertex switched from being at 0, 0, and it's shifted now to negative 4, negative 11. So the vertex moved. All right, that was a little probably confusing. Let's watch another one. Let's do another nice one. X squared minus 6x plus 15. All right, let's figure out what the vertex is. First off, we group these two together. And we make sure that this is a 1. So we're going, everything's great so far. Now our first step is to write the first two, put the blank, do the 15, and do the blank. What do we do to fill in the blanks? We do b over 2 squared. And that's a 6 there for me because our b is 6. 6 over 2 is 3, and 3 squared is 9. So we're going to add 9 in the first one, and we minus 9 in the second one, and it's always that way. We always add first and then subtract. Now, this is a perfect square trinomial, and it factors really beautifully with a negative 3 and a negative 3. So that is x minus 3 times x minus 3, or x minus 3 squared. And then we add these together, and we get 6. Now it's in vertex form, and right here is your hk. So your vertex has moved. It has moved. This means it's right 3, and that means it's up 6. So just remember, when you're looking for your h and your k, the h is always sort of opposite of what it looks like. So it looks like it's minus 3, so our h is positive 3. And the k is always exactly what it looks like. That horizontal shift is always the opposite of what we're thinking, and that vertical up and down is always exactly what it looks like. Alrighty. I have 2 I want you to try. Okay, here's the 2 that I want you to try for me. And we will do some of these in class, and then once you're feeling good about them, we will extend this a little bit. Okie dokie. All right, go complete those squares.